given by Martindale from Technical University of Idaho. So the title of our talk is CSIDH, Unefficient Post-Quantum Commutative Field Action. So please start.
Thank you for the introduction, and thank you very much to the organisers for inviting me to this really nice conference. It's been an absolute pleasure to be here these last 5 days. So yeah, I'm going to talk about CSIDH. Those of you who are here for the school have already seen an introductory mathematical talk on this, and I'm going to quickly go over the protocol for those of you who weren't at the school, and give some idea of the security and some context in this talk as well, I hope. You have the privilege of being the first people ever to see the CSIDH.isotony.org website that's been online since this morning. So there you can find our paper and some discussion on security and related works to CSIDH that have been published, put online since we put our paper online in April. So it's been really nice to see the work that's come out of that. And you'll see one talk after this one, which is also talking about authenticated group key exchange using CSIDH. Okay, so this is joint work with Wouter Kastrick, Tanya Lange, who's over there, me, Lawrence Pani, who's over there, and Joost Reens. And yeah, okay, so, well, this is in case you weren't sure what the CSIDH is. So this is the phonetic spelling of the title of the paper. We all got a bit bored of saying CSIDH all the time, and since we were near the sea, well, I think Lawrence was inspired to start calling it CSIDH, which has seemed to have caught on pretty well, so we've gone with that. Good. Okay, so let's have a little bit of history on Diffie-Hellman key exchanges and isogenies, or something along those lines. So I'm sure basically everyone in the room knows this stuff by now. Well, the Diffie-Hellman key exchange from 1976, and then in 85 we have some Koglitz and Miller do Diffie-Hellman style key exchange using elliptic curves. In 1990 we have group inexponentiation going to group acting on sets. So this might look like an unusual part of a crypto story, but this is a very usual part of trying to extend something to post-quantum, as we'll see a bit later. If you have something in a group and you can sort of move it to a set with some group structure coming from a secret group action somewhere, then you can do some post-quantum stuff, which is, what we're all interested in at the moment, I think. In 94, Shaw gave his polynomial time quantum algorithm to break the discrete logarithm problem in any group. So in particular, the two things at the top there. We're still working on the quantum computer, but that'll come eventually. And then in 97, Couvenier did the first isogeny-based Diffie-Hellman style key exchange with ordinary elliptic curves, although he, at the time, apparently, I don't remember because I was 6, but I've heard that he circulated this among friends that didn't publish it, or maybe, I've heard some dramatic stories, I don't know how many of them are true, but essentially he didn't publish it at the time for whatever reason, and it only came to the light of day sort of 10 years later or so, which we'll get to on the next slide. I couldn't fit everything on one slide. Okay, in 2003, Kuperberg wrote this incredible paper on a sub-exponential time quantum algorithm to attack crypto systems based on a hidden shift. So that's using this group action thing of the Brassard-Young. And basically, if it's commutative group action, then Kuperberg can, with a very gigantic quantum computer, do some cool stuff, which we'll also talk more about later. Okay, so, not 10 years, sorry, what's that? 7 years later, Stolbinev and Rostostov, sorry if there's anyone Russian in the room about my pronunciation, they independently rediscovered Couvenier's idea to use this ordinary isogeny graph structure to do a crypto system. And, then Couvenier was like, oh yeah, that's what I did, cool. So it became CRS, Couvenier, Rostostov, Stolbinov. I'm going to call it CRS from now on, you'll all be glad to know. Then, in 2006, we have this Charles-Goren Lauter hash function from super-singular isogeny graph that David Zhao also mentioned on Monday. In 2010, Childs, Zhao, and Sukharev realized that you could apply Kuperberg's, and Regev, who I've unfortunately sidelined in this history slide, but he will get a proper mention later. So Regev gave a smaller quantum computer version of Kuperberg's algorithm that you pay for some time and memory trade-offs. So they applied it to this CRS isogeny scheme. And, well, I found out on either Sunday or Monday in one of David Zhao's talks that he said he found that rather depressing. So he thought, I'd better create another thing that can't be broken by this Kuperberg algorithm. And that was the birth of CSIDH together with Luca De Feo, which we've all heard about already at this conference. And then this year, or maybe at the end of last year actually, but at least I heard about it this year, De Feo, Kiefer, and Smith came up with some beautiful mathematics to massively speed up the CRS scheme, this ordinary one with sub-exponential quantum attack, which was still really slow, but it was such beautiful mathematics that, well, a bunch of us wanted to look at it anyway and see if we could do something cool. And, well, it turned out that actually we could do something really cool, thanks to Wouter Kastrick, who said, is there a reason we're not using super-singular curves? And then we all said, no, let's do that. So this was the birth of CSIDH, and here he is again, Wouter Kastrick. Most of these slides are stolen from him, so thank you for that history. Good, so that's the kind of my/Wouter's comprehensive history of the lead up to where we are today. And so why would you care about CSIDH? So this was the title of my autumn school presentation actually. Drop-in post-quantum replacement for a Diffie-Hellman scheme. So even more so than CSIDH, this really looks exactly like Diffie-Hellman, and we will see why. I'll show you some justification for that statement shortly. And because it looks exactly like Diffie-Hellman, you can hope to do a lot of stuff post-quantumly that we can do pre-quantumly with Diffie-Hellman. And one example is non-interactive key exchange and full public key validation, which kind of comes naturally together with this scheme, which was previously an open problem post-quantumly. Also, kind of by accident, which was a very happy accident, we had these small keys. So public key is only 64 bytes, which is pretty tiny in the post-quantum world. CSIDH was previously the smallest, and that's 360 something. It's on the next slide, we'll get there. But anyway, so this is really small, which is awesome. And we pay for our tiny key sizes in a slower scheme compared to CSIDH, and especially compared to lattices, which is 1,000 times faster or so. But it's still usable. It's not like waiting hours or minutes or anything like that. It's just 85 milliseconds for one full key exchange. So if you have a small bandwidth application, then this is the most awesome thing in the world. You should all use it. Not biased at all. Okay, good. And the last thing, which is definitely not the least thing, is that this structure, this very Diffie-Hellman style structure, means that it's extremely flexible. So this is a small list that's come from the product of many wonderful people around the world who've been working on applications of CSIDH in the last 7 months since it existed. This C-sign signatures, Lawrence gave a rump session talk yesterday about that and his recent speed-ups, very recent, I think last week or so. So this is Luca De Feo and Stephen Galbraith. They show how to use C-side for signatures, which are, I think the words I use on the next slide are unbearably slow. But that's still nice. I think unbearably slow is 8 minutes, depending on your definitions. But with a quantum computer, you can do it in seconds. So arguably, that's not so bad. The third thing here, so this paper uses CSIDH for oblivious transfer, and the last point uses CSIDH for authenticated group key exchange. I'm not going to spoil, but you'll hear about that in the next talk. Okay, so I've only put this slide in because I think every single talk that I or one of my co-authors has given on CSIDE, somebody says, how does it compare to SIDH? But actually the most important thing on this slide is this blue box at the top that says, apart from mathematical background, SIDH and CSIDE actually have very little in common and are likely to be useful for different applications. It's a very understandable question to say, what about SIDH? Because all of the letters except for one are the same. But it's really like we're playing kind of a different game here, as you can see from this table. So this speed is NIST level 1, so that means comparable to the post-quantum AES 128. And I've got this footnote that says it's a very conservative estimate for SIDH. So this isn't really a very fair comparison, but it's also the only one that I can confidently give you. So these are the parameters from the NIST submission for SIDH. But this 10 milliseconds for SIDH actually gives you more like at least level 2. After speaking to David on Monday, I can say that with relative confidence. And but he also said that you can't really, in a nice way, get a NIST level 1 thing. So this is why this is the comparison. So CSIDE is, significantly slower at the moment. But, well, the next line is our selling point, of course. The public key size for CSIDE is 64 bytes and for SIDH 378. And, well, David also talked already about how you can sort of pay for some time memory stuff with SIDH. You can do some key compression, but then you get a bit slower and smaller keys. So, well, we haven't tried to do that with CSIDE. I don't know if it's possible. Constant time implementation. So at the top it says mostly stolen from Luca De Feo. The mostly is because all I've done is update his table, and this yes on the constant time implementation from CSIDE is as of 2 days ago. And the quick and dirty means that I said to Lawrence, can I put yes in my slides? And he said, oh yeah, just give me an hour. Quickly did a constant time implementation of CSIDE, and now I can put yes on my slides. So thanks. And so this is still, will require lots of optimization to get anything close to the times that we have here. And at the moment it's 6 times slower or so, but I mean, this is also a very, very first draft of the constant time implementation. More details on that later as well. SIDH has a very natural constant time implementation. So CSIDE is only 7 months old, therefore wasn't submitted to NIST. Classical attack is the same. Quantum attack, we'll see later. The security assumption, that's an important thing to point out. So for CSIDE, the security assumption is this kind of sort of classical problem of if you've got 2 elliptic curves, find an isogeny between them. And for SIDH, it's quite a lot stronger than that because you've got 2 elliptic curves and some points on an elliptic curve, which are the image under the isogeny you want to find. And it's shown that there is some things you can exploit there, but you can't, so far, you can't actually break it using that. So it's a kind of, depends on your philosophical standpoint as whether you think this is a problem or not, which I won't comment on. Okay, and so these last 3 boxes, this kind of gives you the state of the art. So the non-interactive key exchange with CSIDE is just completely comes with the scheme for free. For SIDH, there's a complicated construction that means that you can do this in 2 minutes or so, but that's not really yet at a point which we'd want to use, I think. Signatures I already mentioned are unbearably slow for CSIDE and SIDH you have in seconds, but if you have a quantum computer and you want to do a signing, then because there's a bottleneck in the signatures thing which is to do with lattice reduction, you can do that in seconds for CSIDE. And, well, no, I don't think anyone's analysed it for SIDH, but this also doesn't make much sense to analyse it because you've already got seconds for the quantum signatures. If I'm wrong, then please tell me and I will update my slides. Okay, good. Any questions about CSIDE versus SIDH? Yes?
When you say unbearably slow for the SIDH non-interactive key exchange, do you have it? Sorry, very much what is the first result?
I can repeat the question. So
if I remember correctly, for the math book result, It's about 100 or so key exchanges, right? So like 1 second.
So this is about the non-interactive key exchange for people who couldn't hear for SIDH. And so the paper that I looked up said 2 minutes, which is what I mean by unbearably slow, but maybe that's incorrect, I don't know. As far as I know, yeah, it's the mathematical paper. Yes?
So what does it mean, yes, for CCA security compared to Fujisaki Okamoto?
That's a very good question. So that means that with CCA security with CSIDH, you kind of get it naturally, whereas with SIDH you have to combine it with the Fujisaki Okamoto transform. Sorry, I can't hear you. What did you say?
You mean that the Fujisaki Okamoto is not natural?
No, so I mean that it's an addition to the scheme. So it's SIDH plus the Fujisaki Okamoto transform. Okay, good? Everybody happy? Everybody still motivated to listen to the rest of the talk? That's the point? Okay, good. So, what is CSIDH? I've talked about all this stuff, but I better say what it is. Well, it's sort of post-quantum Diffie-Hellman, as I've already said, and I'm going to go through Diffie-Hellman, even though I'm sure everybody in this room knows what it is, because the way I'm going to go through it should hopefully show you how naturally CSIDH is just a generalization of this. So bear with me. So you've got an exponentiation in a group that's the basis of the security of Diffie-Hellman without a quantum computer. Yeah, you know that already. So the idea is to replace this exponentiation with a group action, because what Shor's algorithm does is it exploits this thing on the right here as a group. And so if you have a set, then, well, that exploitation doesn't work, at least. Not obviously. Okay. So this is why the title of our paper has the word group action in it. And so the next thing to do is to figure out how we replace this by a group action. So what's the best way of thinking of exponentiation for this? So as you all know, if you want to compute g to the 13 in a group of size 23, this is a very bad way to compute it. Because, well, you can take some shortcuts and do a lot better. Well, what we're doing is we're actually choosing which cycle to walk along. So all of these lines lie on a cycle. And what I've done here, actually Lawrence made these pictures, so what Lawrence has done here is reordered the nodes so that they all look like cycles. And you can also go backwards along these cycles if you've computed G inverse once. So you get an undirected thing. We reorder the nodes back in the order they were before, then you get this very pretty picture. And, well, all we're doing is we're choosing which cycle to walk along, and they're compatible. If you first do a green one to the right and then a red one to the left, that's the same as doing a red one to the left and then a red one to the right, which with this exponentiation is pretty obvious. That's like saying g squared times g to the 8 is the same as g to the 8 times g squared, right? With some inverses, I guess, but okay. So what we're saying is that we have this union of cycles, so this is just these 4 graphs that then all glued together. And you can sort of walk around this graph and you get something called rapid mixing, so you're at a distinguishably random point in a very short amount of time. And so why am I reminding you how to do square and multiply, which you're all completely aware how you do that? Well, because in CSIDH we actually do exactly the same thing, except we replace our nodes by elliptic curves, and we replace our edges by isogenies. So instead of having an edge being a multiplication in a group, and a node being a g to the x, the node is an elliptic curve, and the edges are isogenies. So there's the elliptic curves in this particular example. So the S of CSIDH is supersingular, and these are going to be supersingular curves of this Montgomery form over F419, and the edges are, in this case, 3, 5, and 7 isogenies. So the blue ones are degree 3, the red ones are degree 5, and the green ones are degree 7. If you're at the school on Sunday and you're not colourblind and you have a very good colour memory, you might think that's the wrong way around, and that's correct, they were the wrong way around, so it's now been fixed, if that's confusing for you. Okay, sorry, so this is the picture, and so what are we actually doing here? We want to replace this exponentiation map, as we said, by a group action on a set. So our set, right, we're replacing the g to the x's by these supersingular elliptic curves in the previous picture. So in this example, we're replacing them by EA y squared equals x cubed plus ax squared plus x over f419. And we're replacing z by some commutative group h, and we're going to see what that is in a little bit. I didn't want to give spoilers at this stage. And how do we move around the cycle? Well, that's the action of some specific element in our group that's acting, and that moves the elliptic curve around one of these cycles. So in this case, it's going to be a 3, 5, or 7 isogeny cycle thing. Okay. So let's just see if we zoom in on this graph. What we're looking at here is this. This is the node E9. Oh, sorry. This is the node E9. This is the node E51. And this line between them, this blue line, that represents a 3 isogeny, which is going to be something with a horrible formula like this. And it also actually represents a 3 isogeny in the other direction, but we'll see more about that in a little bit. Okay, so you've got to imagine that you zoom in on this graph and then you see these isogenies if you see what I mean. Okay. So, what does the key exchange look like if we don't have exponentiation but we have this group action? Well, so instead of having a number to compute, like a equals 13, we have in our exponentiation example, Alice has a sort of path description, which corresponds very much to the group action, to the exponentiation thing. And so Bob also has a secret path, Alice has a secret path, and what does that mean? Well, if Alice walks 1 plus blue, then that's 1 blue to the right, and if Bob walks 1 plus red, then that's 1 red to the right, and then if Alice walks 1 minus green, that's 1 green to the left, and if Bob walks 1 plus green, that's 1 green to the right. And then we continue like that. And then this node that they get to at the end of their secret path, that is that's the public key. So then they exchange public keys, and then all they have to do is walk their secret path again. And then by magic / maths, you end up at the same shared private key at the end. This blob here, which is an elliptic curve. So what makes this work? So what are we looking at again? We have nodes, which are supersingular elliptic curves, in this case over F419. We've got these 3 types of isogenies. And so what are we using when we do this walk? Well, we're using that it's a composition of cycles and that it's compatible. So remember that means that it doesn't matter what order you do the walk in. And we're also using that you can actually do this, that you can compute a neighbor in a specific direction. So we're going to sort of go through what is behind these important properties. So let's first do important property 1. So that's that the graph is a composition of compatible cycles. Okay, I've put reminders. The next 3 slides are things that if you're thinking, I don't know the background for this, then well, you should have come to the school on Sunday. So not my fault. Saturday. When did I speak? Saturday. Okay. Good. So, elliptic curve, if p is greater than 5, when it's defined over fp, is supersingular if it has p plus 1 rational points. So every time I say rational, I mean fp rational. An isogeny between the 2 elliptic curves is a surjective morphism of abelian varieties that preserves the identity. For elliptic curves over a prime field and a different prime L, which is typically small, not equal to p, an L isogeny from one to the other, so this surjective morphism is an isogeny with kernel of size L. And this is very important. if you have an allisogeny between two curves, then it has a unique isogeny going in the other direction, such that when you compose them, you get the multiplication by L map. When I say unique, I generally mean unique up to FP isomorphism. I'm sorry if that's confusing for anybody. Okay, I'm just going to give you 3 seconds or so in case you need to remember these definitions. Good? Oh, the dual isogeny is also an allisogeny. Yes, I didn't say that. Okay, good. So, what's an isogeny graph? Since we're talking about isogeny graphs, we better know what it is. So you have distinct primes, P and L, so we already had those on the previous slide. And the isogeny graph, so that's indexed by L, but it's also over FP actually, containing some elliptic curve E over FP, is the graph with nodes given by elliptic curves over FP, which have the same number of points as E. So if you're supersingular, that's going to be all the supersingular curves, because remember they all have P plus 1 points. And the edges, so the reason it's important that we've got this dual isogeny is because we're only drawing L isogenies, and if we've got a map from E to E prime, then we know we have one going back. So that means we get undirected graphs, which are much prettier, so that's good. So we already saw some examples. We have this G3. So this is the edge of the cycle we saw before, where we did our Diffie-Hellman walk, and the 3 are the blue isogenies. 3 isogenies are the blue isogenies, so these are degree 3 maps. There was a 5 isogeny, so this is a cycle if you reorder the nodes. Well, it's also a cycle if you don't reorder the nodes, but it's less obvious. And we also had a 7 isogeny. And when we did our walk before, what we did is we took the union of those things. So this looks really pretty, but in general, you might get something else. So in general, you can get these sort of trees coming up your cycle, and that doesn't make for nice cryptography. Well, in some cases it does, but it doesn't make for nice Diffie-Hellman key exchanges, maybe. So we have to do something to stop this happening. Okay, what do we do? So we want to make sure that this isogeny graph indexed by just one L, so just one part of the isogeny graph, is a cycle. So on the previous slide, right, we had these things that weren't cycles, and we need to make sure that doesn't happen. And it turns out that it's, this is obvious, equivalently, every node in our graph should be distance 0 from the cycle. This might seem like a bit of a funny thing to say, but the reason I'm saying it is because it turns out that the 2 nodes are at different distances from the cycle, if and only if they have different endomorphism rings. So this endomorphism ring turns out to be a kind of very important thing for the graph structure. So what is an endomorphism ring? I did have a reminder here, but I didn't fit on the slide anymore. We did this at the autumn school. So an endomorphism of an elliptic curve is a morphism from E to itself. So it's abelian varieties. If the word abelian variety scares you, that's completely fine, it scares me too. But you can think that it induces a group morphism. It means more than that, but, well, if it scares you, then don't think about more than that. Okay, so here's an example that everybody has seen in this conference by now, I think. If you take a point on your elliptic curve and you multiply it by n, then, well, that's a morphism, and it's a map from E to itself. So that turns out to be an endomorphism. You can also take the Frobenius map, because our curve is defined over Fp. So that's going to also stay on the curve, and that's an endomorphism. So these things always exist on every elliptic curve over Fp. And this turns out to be pretty useful, because of the endomorphism ring. So the FP rational endomorphism ring, which is the only thing we're going to talk about, so this is different from what Travis was talking about in his talk. An elliptic curve E over Fp is the set of FP rational endomorphisms. So you can also get things over extension fields, but we're just going to forget about those. So here's an example. If P is greater than 3, this was the technical condition, and you have a supersingular elliptic curve of this form that we were looking at before, then it turns out that the Frobenius endomorphism, so that was raising to the p powers, and you compose it to itself, compose it with itself, you get the multiplication by minus p map, right? So remember this is notation for multiplication by something map, and in this case it's minus p. And so what you can do is you can take this quadratic ring here, imaginary quadratic ring, z adjoint square root minus p, and you can just identify an integer n with the multiplication by n map in the endomorphism ring, and you can identify this square root of minus p with the Frobenius in the endomorphism ring. Right, so you get this sort of natural embedding of this, well, if you're a number theorist, nice, easy-looking imaginary quadratic ring into this kind of confusing set of maps that turns out to be a ring. And this extends then linearly to a ring homomorphism, which is kind of what I was saying about it gives an embedding. So what if there's other things here? I mean, this couldn't, I haven't said that this is everything, and it's very often not everything, but if p is 3 mod 8, and p is greater than or equal to 5, and this curve is supersingular, which we already had on the previous slide, then the FP rational endomorphism ring is actually isomorphic to z square root minus t. So what does that mean? That means that the only endomorphisms on this curve come from multiplication by an integer or the Frobenius, right? And that's great because we understand those things, hopefully. Good.
So I have one question.
Yes.
Concerning FP isomorphism natural curve, so we should distinguish or twist, so just using one variable j, so we cannot distinguish or twist pair, but why is it okay for your graph or your system?
Okay, so that's actually a very nice question. But I'll just repeat the question because you only had the microphone at the end. So the question was, since we're only going up to FP isomorphism, why does it still work out with the graph if you take the twist of the curve? So a twist of the curve is another curve that's isomorphic to it, but only over the algebraic closure. And I said that we're only doing things up to FP isomorphism. And so it turns out that for these curves, the twists that you get are then A and minus A. And because they're supersingular, they all have the same number of points. So both this curve and its twist will be in the graph. And actually, it turns out to be a very nice thing, because so the only curve which is isomorphic over FP to its twist is E0, because, well, then A and minus A are the same thing, because A is 0. And if you walk, so the graph turns out to be a cycle, that's a bit of a spoiler, but we'll see that in a minute. But if you walk towards, from E0, and you walk towards EA, n steps, and if you go n steps in the other direction, you actually get to E minus A. So you have the symmetry of the twists in the graph.
I see.
Okay, thank you for your question. Okay, so we've got this nice condition that means that we know everything about the endomorphism ring. Okay, so the title kind of gives away that this is going to be about group actions, and we want to replace this exponentiation map with a commutative group action. So what's that going to be? We need to say what the set is, and we need to say what the group is. I already told you the set, I think, or I told you an example, but you can probably guess it by now. So the set are exactly the elliptic curves that satisfy the things in this blue box. So that's the set of supersingular elliptic curves, y squared equals x cubed plus ax squared plus x over fp, with p congruent to 3 mod 8 and p greater than or equal to 5. And the group is the class group of this imaginary quadratic number field, which you can also think of as the class group of the endomorphism ring of any curve in that set by this blue box theorem thing. Yes?
How is P quantified?
Sorry?
How is P quantified? You says S is a set of all curves with some A's and P's. So
Right, so P is fixed and A can vary. Was that also your question? No. Maybe I can give you my microphone faster.
So when you say that the class group of 7 minus P, do you mean the actual car group is minus p, or is it floating meters?
I mean actual z squared minus p. Yeah. Also an important distinction. Thank you. Any more questions about this? I'm going to tell you the action on the next slide, so or maybe the next bullet point, I don't remember. Yeah? Okay, good. Oh yeah, what is the action? There you go, it's going to be on the next slide. Okay, so, bear with me. The action still takes a couple more things. So you take an ideal. Oh, that's not meant to be a z. It's meant to be this. You take an ideal of the endomorphism ring of one of your curves, which you can also think of as z square root minus p, which I guess is how the z got in there. Sorry about that. So this ideal, you can think of it as a set of endomorphisms. So that's a set of maps from the curve to itself. Maybe I'll write on here in case people catch up with thinking a bit later. Because that's the wrong thing, which could be very confusing. This equals is just in my slides, not in real life. Okay, that's what it should say. Sorry about that. Okay. So then, what can you do? So each of these ideals, each element in this ideal is an element in the endomorphism ring. So, well, that means it's an endomorphism. So it's a map. So it has a kernel. And then you can take the intersection of all those kernels, and, well, by some more magic, that turns out to be a subgroup of the point of the points on E. And if it's a subgroup, well, remember that isogenies are uniquely defined by their kernels. The kernels are subgroups, and that means that we can define an isogeny. Okay, so let's go through that again. You have this subset of maps. You take the intersection of all their kernels. That gives you a subgroup. And then that gives you a unique isogeny, so surjective morphism, from E with kernel HI. Right, so you get from this ideal, which is an element, well, can be associated to an element in the class group in a way that I'll say in a second, and that gives you an isogeny. Okay, so the class group is actually equivalence classes of ideals, and they're not always integral, but there is always an integral ideal in there. So if you don't know what integral ideal means, then you can just ignore this squiggle and everything will make sense. If you do know what it is, then hopefully this will make you happy. So this is then an integral representative of the ideal class I. So this again, it's just this I you can think up here, but with the correction over there. Okay, so then, what's our group action? Well, we take the action of the class group on S to be, you take an ideal in here, together with an elliptic curve in our set, and then you take the image of the elliptic curve under the isogeny that comes from the ideal. And, I mean, we didn't come up with this. This was already studied at least by David Cohen in his thesis, with a slightly different class group, but the idea is the same. I mean, different set. We didn't come up with the idea of applying class groups to this stuff. Anyway, so this is a free transitive group action. So, we're almost at the end, we've almost got enforcer property 1. The nodes of the graph are a set S of supersingular elliptic curves of this form. So this is the things from the blue box like 2 or 3 slides ago. So the things that have nice endomorphism rings. The map is a free transitive group action. The edges are these isogenies that come from the ideals in the endomorphism ring, together with their dual isogenies. And by a little bit more work, but not very much, you get a choice of L's such that each of these GLs is then a cycle, and all of these things are compatible. And that's related to the fact that this is a group action. Okay, so that was what we wanted for our first walking property, right? We wanted a composition of compatible cycles. Good. So, what was our second walking property? Compute neighbours in given directions. So, one thing we need to be able to do for that is be able to choose a direction on our cycle, a plus or a minus we had in the picture. There's a group action again. And for the L's that we choose to make this stuff work, and an ideal in the class group, it turns out that this isogeny that comes from the ideal is an L isogeny if and only if the ideal class is the ideal class of one of these two things. So you can see where this is going, because we want two choices on our cycle, and we've got a plus and a minus here. Well, you can almost see where it's going. And, well, choosing the direction in the graph corresponds to choosing the sign of this ideal. Okay, so to compute a neighbour, we have to compute an L isogeny from a given elliptic curve, right? So each neighbour in the graph is an L isogeny graph. So what do? We find a point P of order L. Then, this is going to be a subgroup of order L, because we take all the multiples of P up to L. And you can compute the isogeny with Veloute formulas, and David talked about that on Monday, so I don't need to cover that. Or Sunday, or both, I don't remember. Sorry, David. Okay, so how do we find a point P of order L? So let's have the same conditions as, well, almost some of the conditions we had before. We have a supersingular curve over Fp and P greater than or equal to 5. Then there's a theorem that says that either this is a cyclic group or it's, well, almost a cyclic group. So what can we do? We can find a point. Okay, that's kind of a very trivial way of saying it, but you can find a point of order either P plus 1 or P plus 1 over 2. Full order as big as possible. Then, for every odd prime, so not 2 because we've got a 2 over here, but for every odd prime dividing P plus 1, if we take P plus 1 over L times this point P of order P plus 1, if you just figure out the group orders, you're going to get a point of order L. And so that's this find a point of order L. And then, because of the fact that this P was an FP rational point, this point of order L is also going to be an FP rational point. And that means that computing the isogeny with kernel given by this thing can be done over FP. And that means that it's fast and awesome. Okay, so to compute the neighbours, let's go over this. This is important property 2. What do? We take the L isogeny graph with odd L dividing P plus 1, like we had on the previous slide. We fix the conditions so that we make sure it's a cycle, as we already did for important property 1. We find a basis of the L torsion, where one of the elements is FP rational, which we can do because of our conditions. Then, 1 is going to be an eigenvalue of Frobenius on the L torsion. And that means that the action of, remember this ideal defined an L isogeny, we saw that a couple of slides ago, and the action of this ideal on E gives an L isogeny in the plus direction. So we've got our plus direction. Now the other eigenvalue of Frobenius is P over L. And if P equals minus 1 mod L, which is to do with the fact that this minus 1 has changed to a plus 1, then the action of L pi plus 1, so that was the other thing that created an L isogeny, gives an L isogeny in the minus direction. So what are we going to do? Well, we're going to make sure that we can satisfy all these conditions so that everything works out nicely. Oh, sorry. Wait, I dropped this into that. Okay. So the question is, for which L can we efficiently compute the neighbours of the supersingular curve E over Fp in its L isogeny graph GL for odd L dividing P plus 1? So we choose a prime of this form, 4 times lots of small primes L minus 1. What do we have then? Well, each of these small primes divides P plus 1. So there's going to be a rational basis point of the torsion as we saw. We choose that means that forces 3 to be 3 mod 8, it's 3 mod 4, so it better be 3 mod 8. So it's a cycle, right? Remember that meant that the endomorphism ring was Z square root minus P. And we had the group action that we saw. And here's -1, there's a minus missing in, mod Li. So we saw on the previous slide that meant that the allied isogenies come from the action of plus a -1. This should be a -1. Sorry. Alright. Okay, given the group action that we had, those formulas give actual isogenies, and all of these choices, and a little bit more, as I've written in this footnote, mean that you can do all isogeny computations over FP. So then it's super fast, well, still 85 milliseconds, right, but super fast in comparison to having to go through extension fields. Okay, so that's the choices that you make to make this graph thing work. Now, additionally, we've got some nice stuff. So you represent the nodes of the graph as this. We've seen this lots of times now, y squared equals x cubed plus ax squared plus x. And what that means, as all the information, in fact this is related to your question from before, all the information is encoded just in this A. So you don't have to do any extra computations or anything. Every node can be compressed to just one FP rational number. And this is pretty awesome because this is actually what gives us the tiny keys, the 64 byte stuff, public keys. So one natural question would be to ask, well, can you just take any curve of this form and you get the thing in your picture? So remember, that means, is every curve of this form supersingular? And the answer to that is no. Oh, spoiler, no. And this actually gives us a public key validation for free. So only about square root of P of all A's in the FP are valid keys. And all you have to do is count points. All you have to do, we've already seen how hard that was from Pierre-Luc earlier this week, but all you have to do is count points to check that it has P plus 1 points. But you don't actually, there's several algorithms to do this. Here's an easy way. You take a random point and check if the order is P plus 1, or something a little like that, other way around. Well, you know what I mean? As this footnote says, this has some false positive chances, but we actually do something a bit better. So that gives the public key validation. Now you might ask,